for the machine learning foundations for product managers. For this presentation, the overview here, we were tasked to build a model to predict the electrical energy output of a combined cycle power plant. This would use a combination of gas turbines, steam turbines, and a heat recovery steam generators to generate power. For this, we have a specific data set, and I've included the source information here. So it includes about 9,568 environmental readings from the different sensors at the power plant. And the columns or the features consist of an hourly average ambient variable. So we're basically assessing on specific features. First one being temperature, represented as T, ambient pressure, AP, relative humidity, RH, exhaust vacuum, V, and we are trying to predict the net hourly electrical energy output represented by PE. I have an example here of what this CSV file looks like, and we're going to leverage this data set. The first thing that we need to do for this course is to really determine what type of machine learning approach is needed, and then to select the appropriate output metric to evaluate the performance in accomplishing this task. For this assignment, I decided to use the regression over a classification model, or at least from the approach side. It's more suitable for this specific type of task for two reasons. One is it aims to predict the continuous value, which is the net electrical energy output based on these environmental variables. And then two, regression algorithms are designed to find the best fit between the input features and the target variable. And then the output metrics that I was looking to evaluate would be the root mean squared error, mean absolute error, and then the other one that I was also going to be including that I wanted to evaluate is R squared. And R squared is typically between 0 to 1, where if it's a score of 1, it means the model perfectly explains all of the variability in the data. It's like saying that the model can predict the outcome perfectly. And then if it's a score of 0 or close to 0, that's like saying the model is not useful at all in predicting the outcome. With the algorithm, we decided to use linear regression. Why? One is that we're assuming a linear relationship between the features, which are those columns, and then the target variable. And then while it might not be the most accurate for complex relationships, it does a pretty good job for just baseline models for comparison. And really the interpretability here is great. So we want to do this first. The goal is if this doesn't look good or we find some issues, we would want to go back. Again, that's why we're starting here first and we're not using a lasso regression or other similar regularization techniques. I don't think we're going to need it quite yet. And I just didn't want to start there. So that's the justification. So let's try it out. So I actually signed up for Vertex AI. And the very first thing you have to do is, since we're manipulating a data set or we're running a model training model against it. So the first thing is to create the data set. So I did a combined, I named it as combined cycle power plant ICETCEE. I selected the regression classification as the data type. And then from here, you hit create. And I've taken some static screenshots because a lot of these steps do take some time. And I wanted to save you from that pain. The second step here is really just uploading that CSV file that I showed you before with the roughly 9,600 records or objectives. And from here, we're going to upload. And then the next step is then once it's uploaded, you can kind of review here to see the distinct values for all of the column names or the features. And then from here, you're going to hit train new model. By training the model, I've selected the objective as regression versus classification. And then from here, you continue down the options. For model details, I gave it a description to say that we're modeling to predict the electrical energy output, PE. And then the target column I selected as PE. One of the parts of the Coursera assignment was then to determine the data split. Luckily, Vertex AI makes this super easy. So from here, I did a random. So 80% of the data was randomly assigned for training, 10% for validation, 10% for testing. I could have manipulated this or adjusted this any way I wanted to, but this felt like a really good way to conduct this first test. The next step here was just training options. I could have established some weighting. So for more regularization or trying to basically penalize features that are not really helping. Again, just didn't really want to start there as part of this first kind of iterative pass. Wanted to just see what the outputs would be for the metrics. And I decided that the optimization objective would start with the root mean squared error. But luckily, and as you'll see in the results, it actually captured some more metrics, which was really, really great. So from here, I started training. Just FYI, it does cost money, number one, but you do get 300 hours of testing with Vertex AI. And then number two, this took about 2.5 hours. So just FYI, it does take some time. So here are the results. So you can see here, there are a few kind of key things to call out. So the root mean squared error score was 3.088. The interpretability may not be simple for a lot of folks, but really all that really means is that because it's a score that's closer to zero, it's pretty good. And what might be a little bit more easier to understand is the percentage error here. And percentage error for the MAPE, this is really close to zero. And that's a really good score. MAPE stands for the mean absolute percent error. That's calculated as the absolute value of the difference between the actual value and the predictions that were generated divided by actual values. So when you sum that up and you divide by the total number of predictions, we get our MAPE value. So for here, because it's closer to zero, that's really, really good. And the metric that made me feel really, really good about this without honestly having to rerun it is the R squared value at the very right. That R squared value is for a model. It's generally between 0 to 1, where R squared of 1 would indicate a perfect model that's able to completely explain all of the variations found in the Y values or the target values. And then a score of 0 would have meant that the model can't really explain the variants that are found in the Y target values. Maybe more simply put, a score of 1 or close to 1, and here it's 0.966. It means that my model here is explaining and predicting the data. And on the other hand, if that was the complete opposite, closer to 0, that would have meant that the model was not doing a good job of explaining the data. One of the last kind of bits of the Coursera assignment is to evaluate which of the features had more importance. And you can see here in this example that the AT, which T is represented as the temperature, and then V, which is the exhaust vacuum. Those are definitely more important when it comes to making the prediction. So if I were to go back and reassess, I would actually put less weight or devalue the ambient pressure as well as relative humidity. Those did not have as much of an impact when making this prediction. It's definitely more important to put more weight on both AT and V for this example. So that is the conclusion of my example here, and I hope you enjoyed it. Thanks. Appreciate it.